on your own after class, sort of in addition to or instead of what your textbook has to say about combining functions. Okay. So it's just a little summary for you to read, and I will hit on the highlights of it as we go through our examples in class. So we're going to start here with combining functions using arithmetic. So we have two functions, x squared and 1 over x plus 1. If I want to add them together, I would just do f plus g, which is x squared, plus 1 over x plus 1. Just make a little substitution. Replace the f with what it equals, x squared. Replace g with what it equals, 1 over x plus 1. And you're done. Okay? That's the sum of the two functions. Just add them together. And then if I want to talk about the domain of the new function, the domain of the new combined function, in order to put an x value into the combined function, it has to be part of the domain of both f and g, right, in order to be part of the domain of the new function. So what's the domain of f here? All real numbers, yep. You can put anything in there. What's the domain of g? All real numbers except -1. So I'm going to make a little number line that shows the domains of each of my two functions. So for f, we said it was all real numbers. So here's my domain of f. And for g, it's all real numbers except -1. So the domain of the combined function is the overlap of the domain of your two functions that you're combining, f and g. So they share a domain, all real numbers except for -1. All the x's that they share as part of their domain is the domain of the combined function. Place where it overlaps. F minus g would just be x squared minus 1 over x plus 1. Done. And the domain, again, is going to be all x's except -1. So you can think of it as the more restrictive of the two domains. Okay, so the domain of the combined function is the more restrictive of the two domains. F times g, so that would be x squared times 1 over x plus 1. And we could actually just do this multiplication. It would be x squared over x plus 1. Same domain. And division would be x squared divided by 1 over x plus 1. And I'm going to simplify it because dividing by a fraction, I could replace with multiplying by the reciprocal of the fraction. So this is going to be x squared times, instead of dividing by 1 over x plus 1, times x plus 1 over 1. And if I write that as x squared over 1, I end up with x cubed plus x squared when I multiply the numerators. I just distributed the x squared to the x plus 1. So that is my quotient, f over g. if you just look at this, what would you say that the domain of that function is? All real numbers, yeah. But because it's a combination of two functions, you still have to go with the most restrictive domain of the two. In order to be part of the domain of the combined function, x has to be in the domain of f and in the domain of g. So the domain still is the set of all x such that x is not -1. So it can trick you sometimes. Sometimes when you do the combination, whether it's addition or subtraction or multiplication or division, the result will look like it has a domain that is bigger than it really is. Okay, and you have to go back and say, no, I can only plug x's in there that I'm allowed to plug into f, and I'm allowed to plug into g. So that's our 5 minutes on function arithmetic. It's pretty straightforward. We're going to move on to something called composition. So this is another way to combine two functions. We can compose them. So sometimes it's useful to use the output of one function as the input for another function. So here are some simple parent functions. So we have the mother function. M of p is going to be the mother of person p. And the father function, f of p, is the father of person p. And we're going to assume each mother and father is unique, ignoring various complexities. Okay. So in your groups, I want you to try to figure out what m of f of p is referring to. What does m of f of p mean? Okay, so m of f of p, well, f of p is the father of the person. So this would be the mother of the father of a person, which is what? Grandmother. M of f of p, this is grandmother of p on the father's side, right? So the paternal grandmother, we call that. So this is a case where we used the output of one function, right? F of p was the output of the father function, and we used that as the input into the m function. So here I have two functions, the same two functions I was working with before, x squared and 1 over x plus 1, and I'm going to compose them. So this little circle, it looks like it says fog, right? That means compose. So it's kind of a superfluous notation. There's no need for us to have invented a new notation, but we did, and your book uses it, so does WebAssign. So whenever you see this, you are going to translate it to read f of g of 3. F of g of 3. So it's just like m of f of p. It just means we're going to plug g of 3 into the f function. So we start on the inside. What is g of 3 equal to? 1 over 4. Yep. So we go to the g, and we say, okay, if I replace the x in the g function with a 3, g of 3, that would be 1 over 3 plus 1, which is 1/4. So now I can replace g of 3 with a 1/4 because they're equal. So this is f of 1/4. And then I can evaluate that. What is f of 1/4? Close. F is the function that squares stuff. What is 1/4 squared? 1/16. Okay, so I'm going to have you try one with a number. I'm going to make up a new one here. I want you to do f composed with g evaluated at 5. Okay, so f of g of 5. So I see this little f circled g. I'm going to translate to that to f of g of 5. So you start out on the inside. You start in the innermost parentheses and work your way out. You say, okay, well, 5, the first thing I'm going to do is plug a 5 into g. So 5 goes into g, and I get 1/6. And then I'm going to replace g of 5 with a 1/6. And then f of 1/6, I'm going to take the 1/6 and plug it into f. And you get 1/36. Okay with that so far? Okay, so now we're going to do it for a generic x. Instead of giving you a number like 3 or 5, I'm just going to give you an x. And so what we're going to come up with is a formula rather than a single number answer. So a general expression for f of g of x. First, translate it to function notation rather than that stupid circle thing. So this says f evaluated at g of x. So before I plugged the x into g and got a number, and I replaced g of 3 or whatever with a number. I don't have a number this time, but I have a formula. I'm going to replace g of x with its formula. So this is going to be f of 1/1 plus x. Then f is the function that squares stuff, right? No matter what you drop into the function machine f, it squares it. So I'm going to take this input, 1/1 plus x, and square it. And we could just leave it like that. That's fine. Now the domain of a composition is a little bit more complicated than finding the domain of function arithmetic. So think of this as two machines, f and g. X goes through the g machine first. You get an output. Then you take that and you put it into the f machine, right? You work your way from the innermost parentheses out. So x goes into g, then you take the result and put it into f. So I'm going to draw it as two machines. So we have G is the first machine, and F is the second machine. So what I'm going to do for F composed with G of X, I take X and put it into G. So X goes into G first. Turn the crank on G, and it's going to take X and plug it into 1/x plus 1. So what comes out is 1/x plus 1, right? That's what comes out of the machine. Are there any restrictions on G? Any X's that I shouldn't plug into G or the machine might jam? -1. So I'm going to put a little note here. X can't be -1 or the machine will jam, right? Then I'm going to take 1/x plus 1, the output from G, and plug it into F. And F is the machine that squares stuff. So it's going to take 1/x plus 1 and square it. And are there any restrictions of things that could jam this machine F? The machine that squares stuff. Is there anything I have to be careful not to plug in? No. There's no restrictions here. So then you take a look at the restrictions on each machine, and you write out your final domain. My domain is going to be the set of all x, such that x can't be -1.
But if you're going to have more than one domain, like if that one had a
Yeah, if this one had a restriction, we would have to think a little bit harder about what the domain would be. And in fact, we have an example coming up where they'll both have a restriction. Here we go. H of x is 1 over x minus 4, and k of x is the square root of x. So I want you in your groups to come up with h evaluated at k of 9 and an expression for h composed with k of x, and then we'll do the domain together. Okay, so let's go over this. So first, translate it to our normal function notation. So h circle k 9, that means h of k of 9. Okay. So then you start with the innermost parentheses and you work your way out. So we start with the 9 and we plug it into k. We get the result and we plug that into h. So when I plug a 9 into the k function, what do I get? 3. So I'm going to replace k of 9 with a 3. And then when I plug 3 into the h function, what do I get? Negative 1. I get 1 over 3 minus 4, which is negative 1. So to do a general expression for h of k of x, first going to translate this to standard function notation, h of k of x. I'm going to replace k of x with its formula because I don't have a number this time, I just have a formula. So this is h of the square root of x. And h is the function, no matter what I plug into it, it's going to do 1 over that thing minus 4. So this is going to be 1 over the square root of x minus 4. Is my composition of those two functions. Now let's look at the domain of the composition of h and k. So the first function is k. So I'm going to make my k machine first. And then that's going to feed the h machine. Okay, so x's go into k. And out comes square root of x, right? Out comes the square root of x. All right, any restrictions on what can go into the k machine? I cannot put in negative numbers. Okay, so x has to be greater than or equal to 0 to go into this machine. Then I'm going to take the result from k, right, the square root of x, and feed that into h. And h is going to do 1 over whatever I feed in. So the square root of x minus 4. Are there any restrictions here? What are my restrictions on h? Yeah, I can't have a denominator in that, a 0 in that denominator, right? So I have to make sure that the square root of x minus 4 isn't 0. I have to make sure that the denominator of whatever this thing produces is not 0. So that means the square root of x can't be 4. Which means that x can't be 16. So I have two restrictions. X has to be positive or 0, but not 16. So my final domain is going to be the set of all x's such that x is non-negative, positive or 0, and x can't be 16. If I wanted to write it in interval notation, which might be how WebAssign accepts it, I would have to say start at 0, go to 16, then union that with 16 to infinity. So finding that 16 is not obvious unless you draw the pictures and think about the function machines. Because if I go to the original functions, 1 over x minus 4 and square root x, the domain of this guy is non-negative x's, and the domain of this guy is x unequal to 4. There's no 16 in there, right? The 16 comes from the fact that the square root of x can't be 4, right? Because you're not plugging x's in there, you're plugging square root of x's in. So it takes a little bit of thought to figure out what the restrictions are in a composition. And it really, really helps if you just draw the picture. And you think, because it helps you remember what's going into that second function. All right, I have a little worksheet that I want you to work on in your groups about composing functions. And we have sort of a real life scenario where you might have two composed functions. These pictures aren't, it's not clear which picture is which. So this is the graph of t. The input is d, the output is t of d. So this is the graph of t. And this one is the graph of f. Input is t, output f of t. So when I want you to estimate t of 500 and t of 1,000, we're going to go to the graph of t. We're going to find 500, which is right here. And we go up to the graph and over and get the output. So t of 500 is 1. And then I can let you do t of 1,000, do that the same way. And then in the next question, they ask you to estimate f of 1 and f of 2. So we're going to look at the f graph. F of 1, you find 1 on the x-axis, go up and over, and it looks like the output is about 250. And then you can find f of 2 and do the compositions on your own. The end. So let's talk about these. So what did you come up with for t of 1,000? 2. Good. And then sentences to explain what these mean. Well, t of d, that means time is a function of distance, right? So 500 is a distance in miles, and 1 is flight time of 1 hour. So 500 miles is a 1 hour flight. And so what does this one say? T of 1,000 equals 2. What does that mean? Yep. 1,000 miles is a 2-hour flight. And we already have f of 1. What is f of 2? About 350. Get that from the graph. And then to translate to words, it was f of t, right? And f was fuel, t is time. So this says that 1 hour uses 250 gallons of gas. One-hour flight uses 250 gallons. And what does f of 2 equals 350 say? 2 hours uses 350 gallons. Why is it that 2 hours doesn't use 500 gallons? If 1 hour uses 250, why doesn't 2 hours use 500, double the amount? Because what? That's a good theory. That's a good theory. But this, I believe they said in the question that this is after takeoff. Maybe. Oh, it doesn't say. It doesn't say. But where's the square root of coming from? The equation, yeah. But why does the equation look like that? Why is it the square root and not just a line. Takeoff is a good yes, but this is also true if we start measuring from once we reach cruising altitude. We started measuring time from when we reach cruising altitude. 1 hour might use 250 and 2 hours would use 350. No idea. 250 gallons of gas weighs a lot. So it adds weight to the plane. So as you burn fuel, you need less fuel because the plane weighs less. Little engineering issue. Okay, so let's look at the compositions. F of T of 500. Okay, well, we know what T of 500 is. We did that in the first problem, right? T of 500 is 1. So I can replace this T of 500 with a 1 because they're equal. So this really is F of 1. And I know what F of 1 is because I did that in the first problem, which is 250. So in words, this says this composition is taking me directly from miles traveled to gallons used, right? My input is 500 miles traveled. My output is 250 gallons. 500-mile trip uses 250 gallons. Okay. I had an intermediate step, right, where I calculated that it would take 1 hour. But the input is 500 and the output is 250. So this is a sentence telling me that a 500-mile trip uses 250 gallons of gas. And I had an intermediate step to help me figure it out, but the final sentence doesn't say that. That's the purpose of doing the composition. All right, so then the next one, F of T of 1,000. What would that be? F of 2, which is 350. So if I wanted to write a sentence about what that means, what would it say? You got it. A 1,000-mile trip uses 350 gallons of gas. Okay, so then this last one, we actually gave you an equation for each of the two graphs, and we were going to repeat them again using equations instead of graphs. So F of T is 250 root T. And T of D is D over 500. So I'm going to jump to the composition because the composition answers the other two questions. So I wanted F of T of 500 and F of T of 1,000. Okay, so F of T of 500. So I should start by evaluating T of 500, this time using my equation instead of the graph. So what is T of 500? 1. Yep. If you plug a 500 into the function for T, you get 500 over 500, which is 1. So I get F of 1. And then what is F of 1? 250. 250 times the square root of 1 is 250. So I get the same answer using the equations as I did using the graphs. All right, let's try F of T of 1,000. Well, what is T of 1,000? 2. Yep, 1,000 over 500 is 2. And what is f of 2? Well, it would be 250 times the square root of 2. Let's see what that is. 2 square root times 250. 353.55. Which is very close to what we got when we estimated using the graph. Okay. Any remaining questions? All right. All right, so I want to find f of t of d. So I don't have numbers this anymore. I'm working just with symbols. So I'm going to replace t of d with its formula. So this is going to be f of d over 500. And then the f function is the machine, whatever you put into it, it's going to square root it and multiply by 250. So under that square root, I'm going to put d over 500. And that's going to be my formula for how to calculate fuel usage as a function of distance traveled directly. So now I could plug any distance into this formula and get fuel usage out without having to go that intermediate step of calculating time first. So that's the advantage of writing a composition of two functions.